Okay, so here we're going to see a proof that there are infinitely many prime numbers. And this is a proof that's all over the place. I'm sure there's tons of videos on this. It's in tons of textbooks. But I'm putting it in anyway, and I'm doing this for several reasons. One is just, I just like this proof. It's so beautiful. But another one is that it's a really, really good introductory proof for someone who's sort of thinking about getting into math or isn't that much into math. And it's a great place to start because it just uses some sort of basic divisibility things. You don't need any fancy machinery at all. And this is one of the more accessible proofs of a really far-ranging result, which is that there are infinitely many primes. It doesn't seem, to people who don't do a lot of math, it doesn't seem like it's possible to prove this, because no matter how many you find, you haven't found infinitely many. So how are we going to prove that there are infinitely many primes? We're going to do a proof by contradiction. And if you're watching, if this is the first of my videos that you've seen, you'll notice the wonderfully childish handwriting here. I have to say it's made a little bit worse by the stylus that I'm currently using. It doesn't have a great tip. There's a better one. In other ones, it's better. But right now, this is my bad pen. So I'm going to blame it on that. Proof by contradiction. What are we doing here? We're going to suppose, we're assuming that there are finitely many prime numbers, and then we're going to use this assumption to derive a contradiction. The great thing about proof by contradiction is, one, that it gives you a starting place. You don't know where to begin a proof. You're trying to prove something's true. Well, suppose it's not, and then you have something to work with, and then from there your job is just derive a contradiction, get any contradiction. So we're going to find something which is contradictory will have to be true if there are only finitely many primes, and that means that there can't be finitely many primes. And just like that, we proved there are infinitely many of them. It's that simple and easy and beautiful. So let's call these primes, if there are finitely many of them. I'm going to call them P1, P2, all the way through Pn. So we're supposing that there are n of these primes, P1 through Pn. And this allows us to say, okay, well, if this is true, I'm going to construct the number 1 plus P1 times P2 all the way through Pn. This is the product. It's the product of all these primes, the pi's as we call them. We'll see this in just a second. We index these. We would call these pi such that 1 is less than or equal to I, which is less than or equal to n. I is the index. It's kind of a short way of referring to these things. This number is, well, for one thing, it's bigger than pi, and this is where the indexing comes in, for all 1 less than or equal to I, less than or equal to n. And in other videos we explain this in more detail. But if you haven't seen this before, this upside down a, that means for all. That's the universal quantifier for all. There's also this backwards e that means there exists. Don't worry about that too much for now if you haven't seen it so far. But this is bigger than all of these pi's, right? It's bigger than any one of them, because all primes are bigger than primes. All primes are bigger than 1. So if you multiply them together, they just get bigger. This is bigger than any of the pi's for every single pi. And so we construct this number. We add 1 to it, and then we say, well, what about this thing? Is this prime? Is this prime? Well, if it is, then since it's bigger than all the pi's, it can't be one of the pi's. So that would mean that there are actually n plus 1 primes. That would contradict our assumption that there were only n of them. So that means it can't be prime, given this assumption. That means it is divisible. If it's not prime, it's divisible by 2 numbers which are less than it, at least 2 numbers which are less than it, and in particular, it is divisible by a prime. We'll just call this one, say, Q. We'll call that prime Q. And this actually is something that comes from the fundamental theorem of arithmetic, which if you haven't seen the video on that, you can check that out. I'm just realizing that if people are watching this one as their first number theory video, you might not have seen the one about, or you might not be familiar with the fundamental theorem of arithmetic. It's kind of the starting place of number theory, one of them. And it just says that every number is a product of prime numbers. And this kind of makes sense. There's actually a proof of this, but just intuitively, if a number is prime, then it's the product of itself and 1, although 1 is not prime. So it's just so fundamental theorem says that it's either every positive integer is either a prime or it's a product of primes. And if it's not prime, then it's divisible by 2 or more numbers. So you divide it into those 2 numbers, you factor it, and then each of those is either prime or they're divisible by something else. You could just keep doing this until you hit primes at the bottom like that. So hopefully you believe me about this. This means that it will be divisible by a prime q. And also I'm realizing, since I was thinking what to call this so that it won't be one of the primes on the list, but actually the idea of the proof is, I'm kind of tired, by the way, right now. This is what I do in the middle of the night when I can't sleep. I make math videos. So it's divisible by a prime, say pi. And the reason I can call this pi for one of those primes is because our assumption at the beginning was that these are the only primes. There are only n primes, so it has to be one of those, right? If it's divisible by a prime, these are the only existent primes. So it will be divisible by pi, and then we'll call the quotient q. We'll say it's divisible by pi, so it's pi times q. And this is going to be for some q in the positive integers. And this is where my sleep-deprived brain was getting the q from, I'm realizing, as I do it. Okay, so let me rewrite this, and I'm just going to rewrite this product so that to throw in the qi, because it's somewhere in there. We don't know which one it is. So this is 1 plus p1 times p2 all the way through pi, all the way through pn. That's equal to pi times q. So here's our friend pi in the middle there. There he is again. And these are the other primes, and that's q. But then what can I do? Well, I can subtract the product of p1 through pn from both sides, and I'll get 1 is equal to pi times q minus p1, p2, all the way through pi. Maybe you can see where this is going. All the way through pn. And then from this stuff over here, I can factor out our friend pi. I can say this is pi times q minus p1, p2, all the way through pn. And actually in the middle here, I'm going to put a pi hat. This is a math notation thing that shows that this one isn't on the list here, right? We could have written this divided by p, or the product divided by pi, but I like the hat notation for some reason. Pi hat means that one is no longer on the list. We're putting that in to show that is no longer on the list. And here we have our contradiction, which is one of the great points during a mathematical proof, because you get to draw this cool dragon tail thing, and it's actually called a dragon tail. It means it's a contradiction. This is a contradiction. Why is that? Because this is impossible, right? 1 is only divisible by 1 and -1. The only 2 factors of 1 are 1 and -1, right? I can write 1 is equal to 1 times 1. I can write it's equal to -1 times -1, because a negative times negative is a positive. So that's our contradiction. 1 is not divisible by any primes. We got a contradiction out of it. And just like that, our assumption that there were finitely many primes must be false. And we can say, therefore, I write our little triangle of dots, there are infinitely many primes. Isn't that cool? With just sort of basic divisibility and some reasoning, we proved this very sort of surprising, far-reaching result about the natural numbers, about the prime numbers particularly. By the way, this is the part of the video where I go on a sort of little rant about how nice number theory is and how nice proofs are. I swear I don't do this in every single one of them, just in sort of the introductory ones where people are seeing it for the first time. And I bring up this. You've probably heard this before if you watch other videos, but that's a terrible color to put in this one. Gauss's quote, that math is the queen of the sciences and number theory is the queen of math. It's a great starting place for people who are getting into math for the first time, which I think everyone should do, even if you had a bad experience with it in high school. It's a really beautiful thing, or in junior school, which somehow in the hands of people who teach to children, unfortunately, it turns into a chore. Somehow it turns into this thing that people get a mental block against. I was like that in junior school. I hated math. I had a really terrible, unpleasant experience with that. And then I didn't actually start doing math until I was an adult and I was in university, and I switched majors in the middle of my university degree. I switched from philosophy into math, and just absolutely loved it once it was sort of taught properly, once they sort of taught it in a way that allows the beauty to come out, and that the way that you get the beauty, the way that you see the beauty in math is by really understanding stuff. And that's in my view the main thing that's sort of missing from junior school. Is they just tell you, here, this thing is true, memorize it, accept it. I'm not going to tell you why it's true. Maybe I don't know how to tell you why it's true. If I just told you there were infinitely many primes, how impressive would that be? How nice would that be? It's the reasoning, it's the beautiful sort of clean, pure, sort of simple reasoning that gets you to these amazing results. That's the really beautiful part of math. One more quote, and then probably most people aren't watching anymore, but one more quote, and then I'll end it. Archimedes said something along the lines of, math only reveals its beauty to people who, or reveals its secrets to people who study it for the pure beauty, for their own inherent interest, or something like that. Take the gist of that without getting the exact words, please. The idea is that if you actually really want to understand things, if you're looking for the beauty, if you're not just doing it as a chore, as something that you have to do, it can be this really wonderful, amazing, fascinating thing. And so I hope this video, and there's a couple others that I did sort of in the same vein with a big rant at the end, hopefully these kind of inspire people to see math as something enjoyable and beautiful and fun, rather than a chore, something that you sort of have to do.